Okay, so in this video we're going to solve circular functions. And this is something you probably only learnt in year 11 onwards. And it can be quite tricky the first few times, but once you get used to the general process, it's usually fairly straightforward and very rarely does it deviate from the same main idea. There are two main ways to solve our circular functions. Both end up with the same result. Both are equally valid. I'll do one video with one way and a second video with the other way. Same notes, same examples though. But it is absolutely imperative that you know your exact values. So here's the exact value table in front of us here. We must know these. Otherwise, trying to solve equations with circular functions by hand is going to be a nightmare. So you need to know those ones. So here are the main ways to solve. The first three steps for both cases, it starts the same way. So in all cases, get sine, cosine, and tan by itself. Then you define the reference angle or the base angle, which comes from our exact value table up here. And then we're going to find all the solutions in the first period or first rotation between 0 and 2 pi for the sine, cosine, or tan that we've got. This is where it deviates. And in this video, I'm going to look at the left-hand side, which is we're going to solve for x in the first period, and then I'm going to add and subtract periods to find all the solutions in the domain. This is my preferred method, but both are valid. So let's see how it works. So we've got 2 cosine of 3x equals 1 minus 1 equals 0 between 0 and 2 pi. Well, first of all, I need to get cosine by itself. So to isolate cosine, you're going to have cosine of 3x equals 1/2. There's our first step. Our second step was to think of our reference angle or our base angle. Now I'm going to stick away from writing x because x is in my equation. I'm not going to write x now. I want to find what angle I'm dealing with. Well, I know from the exact value table, I can scroll up there and have a look, or you can remember it in your mind, that pi on 3 is the angle which gives me half when I'm using cosine. That's important. Now, when I'm dealing with this half, I'm trying to find things now. I'm up to a third step here, trying to find all the solutions in the first period. Notice I have cosine of 3x equals positive 1/2. We have to remember where cosine is positive. Now, cosine is positive in quadrant 1 and quadrant 4. And the size of the angle measured here from each axis is pi on 3 in size. Now that's important because of symmetry properties. So we're going to always try to, in this question, trying to get pi on 3 from the positive x-axis. So my third step in this one was to find all the solutions in the first period. So the first period here, we're going to have 3x equals pi on 3, comma. Now remember with circular functions, we measure from the positive x-axis anti-clockwise. So to go all the way around there requires us to go all the way around to 2 pi and then come back this pi on 3. So we get 2 pi minus pi on 3, which gives you pi on 3 and 5 pi on 3. Up to this point, for both methods, was still the same thing. Note at this point that this 3x is exactly the same thing there. That is really important that you leave it as 3x. Don't divide your base angle by 3. You leave it as pi on 3. Once everything's substituted in, it's all set up, then we start dividing by 3. So this is where we're going to divert. This method here, on the left-hand method from up the top, this is where we now divide by 3. We have found two solutions in the first rotation. I'm now going to divide by 3. That gives me pi over 9 and 5 pi over 9. And I put a little annotation here in our first period or in one period. The thing is though, how many periods am I required to find? Well, let's have a look at our original domain that we're given. We're given between 0 and 2 pi. And we know the period of a cosine graph is given by 2 pi divided by the n value, which is 3 in this case. So 2 pi over 3, this is 1/3 of 2 pi, which means we're dealing with 3 periods. 1/3 of 2 pi, this gap is 2 pi, so we've got 3 periods in total. At this point now, we've got solutions in 1 period. I've got to find 2 more periods. I'm going to add periods on top. Before I do that, I'm going to do a couple of things in terms of common denominators to make my life a whole lot easier. So therefore, x equals pi over 9, comma, 5 pi over 9, comma, and now I need to add a period to the pi over 9. Now the period, I want to write with a denominator of 9. That makes a whole lot easier, which is 6 pi over 9. So now I do pi over 9 plus 1 period, which is 6 pi over 9. And I do 5 pi over 9 plus that period of 6 pi over 9. Now I did say I wanted 3 periods, so I've only done 2 so far, 2 sets of 2, so I'm going to do one more at the end, one more set, so pi over 9 plus a second period, so 2 lots of that. Hopefully I fit it in. And 5 pi over 9 plus 2 lots of 6 pi over 9. So I've added 2 periods because I needed 3 in total. A quick check also will enable me to look at my domain, and my domain is between 0 and, if I write 2 pi with the same denominator as all of these, it's going to be 18 pi over 9. So I've got to make sure my biggest value here, this last one, doesn't go bigger than 18 pi over 9 to make sure all my solutions have been met. So we'll see that in a minute. Let's simplify all these. So get pi over 9 and 5 pi over 9. That hasn't changed. That's the same as what we had over here. That's our first period. And now we add 6 pi over 9. So you have 1 pi plus 6 pi gives you 7 pi divided by 9. And the 5 plus the 6 gives you 11 pi over 9. You have 2 times 6 is 12, plus 1 is 13 pi over 9. 2 times 6 is 12, plus 5 give you 17 pi over 9. And notice we had to go up to 18 pi over 9, and we've got 17. If I add another period, another 6, you get 23, too big. If I add another 6 to this one, we get 19, it's too big. So we've got all our solutions. Let's do 2 more examples. I'm doing sine, cosine, and tan, one of each. Right, next one. We want sine of 2x by itself. That's our first step. We want to isolate sine of 2x. And we get root 3 on 2. Now we've got a negative there. We're going to deal with the negative in a minute. But what's our base angle? Well, to get a base angle, what angle gives me root 3 on 2? I'll go back to the exact values. I think about them. The angle I'm dealing with is again pi on 3. So I'm again dealing with pi on 3. Let's have a look at all the solutions in the first period. 2x is coming down. It equals, again, remember this whole 2x comes down until I have found all the solutions in that period. Now, sine is negative where? We've got negative root 3 on 2. So sine is negative in this axis here and this axis here. Remembering that angle they're measured from the axes are both going to be pi on 3s. That's the size of the angle. To get the first one, I've got to go around pi plus another pi on 3, don't forget. And to get this other one, we did the same a minute ago. It's 5 pi on 3, which was because we had 2 pi minus pi on 3. We simplify that, you get 4 pi on 3 and 5 pi on 3. And now we divide by our 2, which is 4 pi on 6, which does simplify the 2 pi on 3, but I'm going to leave it like that for now because it helps me with all the denominators the same. At the very end, I'm going to simplify that down. So we've isolated sine, we found our reference angle, which quadrants it's all in, and now we've divided by 2. All right, let's find all our solutions. That's only one period. We're going to see how many periods are going to be. Well, we know the period of our graph is 2 pi divided by this 2, which gives you pi. And you hopefully notice we're going from negative pi up to 2 pi. We've gone up 3 pi. So from there to there, we got plus 3 pi. So we again have 3 periods. I should have chosen ones that didn't have so many solutions. And then in here, we're going to find all our solutions. But before I do that, let's write the period over 6 pi, sorry, over 6 to match all these ones. So 6 pi over 6 there. And now we're going to find our solutions. So x equals 4 pi and 6, 5 pi and 6. We're going to add a period. So plus 6 pi and 6. And we're going to add a period to this one as well. Now, before I go any further, I'm going to pause for a minute. Notice this second one is 5 pi plus 6 pi. So it's 11 pi over 6. And my domain is just a negative section, so I don't want to forget that. So let's quickly check this. If I want to write negative pi with the same domain, it's negative 6 over 6 pi. And the 2 pi becomes 12 pi over 6, like that. Well, the 11 pi over 6 is almost there. If I add anything more, it goes too far. But notice none of my solutions have negatives, so I also want to allow for negatives. So these two here in the first period, these two here in the second period, but what I want to do, I want to go back before this one and go backwards around the unit circle, because remember, going around backwards, unit circle going backwards, you get negative angles. So I want to subtract pi and 6 from, sorry, 6 pi over 6, one period from the first solution and the second solution. So from both the solutions in the first period, I've now subtracted. At this point, I'm going to simplify them all. So I get 4 pi on 6 minus 6 pi on 6 is negative 2 pi over 6. I'm just going to do it in number line order. 5 pi minus 6 pi is negative 1 pi on 6. That's these two at the end done. Then we're going to have the two from our first period that we found out. And then we're going to have all these ones. So 4 pi on 6 plus 6 pi on 6 will give you 10 pi on 6. 5 plus 6 is 11, so 11 pi on 6. And then to finish it all off, we're going to end up with negative pi on 3. We always must simplify our fractions. 4 and 6 cancel out to 2 pi on 3. And 10 and 6 cancel, so you get 5 pi on 3. And there are our solutions. Final option, final example, sorry, is tan. We haven't done a tan one yet, so let's do a tan one. We're going to isolate tan, so let's subtract the 5 first. 1 minus 5 is negative 4. And then tan of pi x will equal 1. Now we're going to go back to our exact value table. What is our base angle? Well, tan of what gives you 1? That is pi on 4. And it's positive, so let's see which quadrants it's in. Now tangent is positive there and positive there. So I've got pi on 4 there, which is nice, and I've got pi on 4 there. So bring the pi x down, and you end up with pi on 4, and you end up with pi plus another pi on 4. Now, technically with tan, this is actually 2 periods. Remember with tan, the period is only pi over n, not 2 pi over n, but it doesn't hurt to find the extra one in this case. So now I'm going to divide by pi, and I find 1/4 and 5/4. Are they all solutions? Well, no, I can clearly see from the domain I should have negative values, and this 5 over 4 might actually be too big. So let's check our period. The period of our graph, for the tan graph, remember, is pi over n. In this case, n is pi, so pi over pi, which gives you 1. So once again, we have 3 periods. I did do that on purpose, I promise. So we now have the values x equals 1/4, but this 5/4, it looks too big. Let's have a look up here. The domain, negative 2 is the same as negative 8 over 4, and 1 is the same as 4 over 4. So this 5 over 4 is too big. That's a problem. We don't want that, do we? So 1/4. Now if I add a period, if I add 1/4 plus 1, I get back to the 5/4. So I don't want to be adding anything in this case. I need to subtract. So 1/4 minus 1, that's subtracting 1 period. And then we're going to subtract 1 times by 2, a second period, because we're doing 3 periods. If I simplify that, you should find you have -7/4 pi. So just -7/4. This one here is -2. Add a quarter back, gives you -7/4. This one here, 1/4 minus 1 is -3/4. And we have 1/4. I could, of course, have written this as 4 pi/4, but being a whole number of 1 shouldn't cause too many issues. If I check this with my domain, if I add 1 to this, I get too big. If I subtract 1 from this, I go outside the -8. So there are my solutions. And that is how you solve circular functions in that particular method. I'll do another video with our second one very soon.